So today we are going to start with the topic of antenna arrays. Okay, first we'll just have a brief introduction of what exactly an array is, what is the need of array, just have a brief idea about what is done exactly in antenna arrays to realize what is called as the higher gain, and then we'll talk about different feeding techniques, then different configurations using those feeding techniques, and then a comparison between uniform and non-uniform array covering binomial distribution and triangular distribution for antenna arrays. Okay, so let's begin with basics of gain of the antenna and what is the requirement of array. Now if you talk about applications of antenna in Wi-Fi applications or any wireless application, very important parameter is the antenna gain, because that ultimately decides in which direction and how much a power is being radiated by the antenna. In long distance communication, where you need to communicate maybe from a satellite to the ground station or from the aircraft to the ground station, or any multiple such applications where range required is very high. In such cases, if you have an antenna which has a very small gain, maybe around 2 to 3 dB as offered by your dipole, or maybe 6 to 8 dB as offered by your suspended microstrip antenna. So in those cases, you will not realize what kind of a, you will not be able to realize that kind of a range which is required. Just recall your Frisch transmission line equation. In your Frisch transmission line equation, ultimately it relates transmitted power to the received power. In that, very important parameter is GT and GR, that is the gain of the transmitter and the receiver. So to establish a long distance communication, you need to have a larger antenna gain. Now here I have written a basic equation of the antenna gain, that is 4 pi AE by lambda square into eta. AE is the effective aperture area of the antenna, lambda is your operating frequency, and of course eta is your total antenna efficiency, considering the input losses, considering the losses taking place in the antenna structure. So I am referring that as a total antenna efficiency. So here, if you look at this equation very carefully, if I want to increase the antenna gain, what I need to do is either emphasize on getting maximum antenna efficiency. Suppose I ensure that 100% efficiency is achieved. So the only two parameters which are left with me are basically the effective aperture area and then lambda, that is the operating frequency. Now just as a layman, suppose I want to increase the antenna gain, what I will do? Okay, just decrease the value which is present in the denominator. So if you reduce lambda, naturally you are going to increase the gain. And that is one of the reasons that for most of the long distance communication, we use antennas which are operating in higher frequency band, that is above 2 GHz, above 3 GHz, or even above that. So where lambda is small and you do realize higher gain eventually. But see, this is not a practical solution, because you cannot have all the applications running at very high frequencies. You need to have the antennas which are operating maybe in GSM band, but you need to have a larger range. So in that cases, really speaking, changing lambda is not a solution, because ultimately that changes your operating frequency, that has a direct impact on designs or the antenna dimensions. So definitely this is not the case. Now let's look at the other parameter, that is antenna aperture. And now antenna aperture, actually speaking, it can be the physical or the electrical aperture of the antenna. Remember, electrical aperture of the antenna is related to the physical aperture depending upon the polarization and the area of the antenna facing the incident electromagnetic field. Okay, so here I want to increase the antenna aperture. Now one way of looking at the same problem is just go on increasing the antenna dimensions. But remember, when you increase the antenna dimensions, your operating frequency is going to change. Lambda is going to increase. So that is not going to serve the purpose of increasing the antenna gain for a given frequency. So definitely, I need to change the effective aperture area of the antenna by keeping lambda constant. And that led to the concept of the design of antenna arrays. So I will just define what exactly an array is. It is basically an electrical as well as a geometrical grouping Okay, it is electrical and geometrical grouping of the antenna of individual sources, okay, which are having same characteristics. I'll just repeat, it is basically the electrical and geometrical grouping or the arrangement of the individual antenna elements which are having same characteristics. Okay, so they are grouped together so that the effective aperture as seen by the incident wave is increased. I'll just give you an example. Suppose you have a dipole radiator here and the wave is incident onto that. But if I have an electrical combination of that dipole radiator such that additional dipole radiator is appropriately spaced with respect to the first radiator and appropriately division of the power or the combination of the electrical signal to those two is given, then to the incident or the distance field, the effective aperture which is seen by the antenna or by the observer or the incident field is now increased. So this is what I have done. I have appropriately grouped the two antennas, individual antennas together so that effectively for the distance observer or the incident wave, area is increased. Individual antenna is working at a given frequency. So two antennas are still working at given lambda, that is the operating frequency. But to a distance observer, I am increasing the effective area as seen by the antenna or seen by the incident field. That is what is done in increasing the effective area of the antenna or in case of antenna arrays. So it is antenna arrays is basically electrical and geometrical grouping. Now why electrical term comes? Because lot depends upon what amplitude is being fed to these antennas or how the amplitude is gathered from these antennas. Okay, what is the spacing between them? So what is the phase difference between them? So lot of electrical as well as geometrical parameters are coming, whether they are arranged only along the linear axis or whether I am arranging them in a planar axis. So lot of variations are possible. So that's why I use the term electrical and geometrical grouping of the individual antenna elements, that is forming the antenna array to realize particular gain. Okay, so of course in the end I'll try to explain one such practical application of which is being used and which has a very large antenna gain. So in the end of this lecture I will explain you or give you an example of a practical application of the antenna arrays, which is a very interesting case to understand. Okay, so here we have rather introduced the concept of antenna arrays. We have introduced why antenna arrays are required, what is done in array, how the antenna effective aperture area is increased. Now just to put on record, there are following parameters which are there which controls the antenna radiation pattern of the array. What is that? Definitely the amplitude which is fed to these two antennas. Okay, then what is the phase signal which is introduced between those two antennas, what is the distance between them, how the antennas are arranged, means what, whether my one antenna is arranged vertically and whether the second antenna is still arranged vertically or in the different direction, and whether these two are of the same type, means what, whether one is antenna is dipole, other one is loop. So all these parameters decides what output you are going to get from antenna arrays. Remember, apart from amplitude, apart from phase, apart from distance, the last two parameters which I talked about, they are very crucial. You cannot have an antenna array which are having antennas which are orthogonally placed. Means what? One is radiating or receiving a vertical polarized signal, other one is receiving a horizontal polarized signal. That array cannot be formed. Okay, so polarization or the radiation characteristics of the antenna should be the same, right? So here the two antennas should be identical. That is another point. Means what? If I am having a dipole, I cannot have an array of the dipole with the loop antenna or a Yagi antenna. I should be having a same antenna characteristics. That means apart from amplitude, apart from phase, apart from the distance between them, you can literally play with these three parameters, but you cannot touch the antenna radiation characteristics and the type of antenna. That's why I said same antenna characteristics. So it is an array, although you have a geometrical grouping, although you have an electrical grouping, and then make the arrangement to form certain structure. But remember, the antenna should be having the same characteristics in terms of radiation pattern, in terms of type of antenna, which is being used. So this is the concept of array, and these are the parameters which controls the array. Based on that, definitely in the end we will talk about uniform array as well as non-uniform array. Okay, so now having done this, now we will go to the microstrip antenna array concept. Remember, advantages of microstrip antenna are being exploited to larger extent while forming the antenna array. Why? Because they are planar structures. Okay, if you just imagine the array of dipole, array of Yagi-Uda or any other antenna, it becomes bulky in nature. It becomes widespread structure. In case of microstrip antenna, as the single patch is a conformal structure, the entire antenna array is going to be a conformal structure. Okay, so that's why now we will now emphasis on the design of microstrip antenna array. Okay, so now we will talk about microstrip antenna array. So here you have your coaxially fed rectangular microstrip antenna. Now whatever discussion which I am making with respect to the rectangular microstrip antenna, similar discussions are valid for other shapes of the microstrip antenna which are forming the antenna arrays. Right? So here I have a coaxially fed microstrip antenna. As we have seen in the basics of microstrip antenna, the introduction part, coaxial feeding technique has a limitation in terms of their usability in the antenna arrays. Because remember, coaxial feeding technique, the antenna is fed from the bottom. So it is really difficult to have a planar connectivity for the antenna if you have multiple elements to be connected. So coaxial fed antennas, they are not at all used in microstrip antenna array. What we use is the microstrip line fed antennas. Now when we introduce a microstrip line fed antennas, one disadvantage with this microstrip antenna array remains that we are not utilizing same substrate parameters for the microstrip line and the microstrip antenna. So that disadvantage remains with all microstrip antenna arrays, and really speaking, I have not seen any array where a substrate parameter utilization is done where a different substrate is being used for microstrip line against the microstrip antenna. Because we have two different sections, remember, a microstrip line and a microstrip antenna. So here we are not at all differentiating or optimizing the substrate parameters. What we are doing here, to the best possible extent, we are using the substrate parameter which satisfy the requirement of the microstrip antenna. So we are using maybe a lower dielectric constant, a RT doroid substrate, or maybe Erlong substrate, maybe foam substrate. Those kind of substrates are used to design a microstrip antenna array. Right? So now this is talking about the substrate parameters. Now let's see what about the feeding. So basically we are going to use the microstrip line feeding technique. There are three different variations of microstrip line feeding techniques which we have learned. This is called as the inset. This is called as the inset microstrip line feeding. As we know, what is done, this point is basically a 50 ohm point on the patch. So the 50 ohm microstrip line is being positioned by cutting a small inset or a slot at this point so that the impedance matching is realized. And then you can use this to form the array. How it is done, that we will see later. But this is the structure which is used for forming a microstrip antenna array. And that one feeding technique is inset microstrip line feeding technique. But remember, this has a lot of disadvantage. Means what? You need to cut a slot, decide upon the feed point rather accurately, and then connect your 50 ohm line. So to simplify this, you have another feeding technique where you are not cutting any slot. But I am putting a microstrip line right at the edge. So what is done? Definitely there is no need to cut a slot. Whatever is impedance measured at the edge point, whatever is impedance which is present at the edge point, same value of the impedance for the microstrip line is considered. Okay, because then you have a matching between the microstrip line and the microstrip antenna. There is no mismatch, and then you can have a microstrip line fed antenna array. Okay, but remember, this is a very high impedance line. For example, when I talk about a microstrip antenna edge impedance, it definitely varies with respect to the substrate used. Suppose I use a FR4 substrate, definitely a rectangular microstrip antenna will offer me the edge impedance of around 200 to 250 ohm, right? then you need to design your microstrip line feed for that edge impedance. And then when you have a higher impedance of the microstrip line, then the thickness, okay, the thickness of the line decreases. They are not realizable, okay, because it may just turn that the thickness of the line on a given substrate thickness may be 1 mm or 2 less than that. Remember, realizing that much finer microstrip line width on that structure is difficult to realize. Hence, that technique is not used. What is more optimally used in microstrip antenna array is this kind of a technique, where what is done, there is no inset slot cut. There is no inset slot cut. What is done, you have a high impedance microstrip line. Okay, you have a high impedance microstrip line, or rather a quarter wave transformer. Quarter wave transformer. What is done here at this point, the impedance present is basically a edge impedance of the microstrip line. Say that is treated as ZL. Okay, then this is definitely the length of this section is quarter wave length, that is lambda by 4. What is done? This is edge impedance that is taken as ZL on that quarter wave section. What is required at the input side is 50 ohm, right? What is required at the input side is 50 ohm. Okay, so that becomes my ZL. Then characteristic impedance of that particular microstrip line, which is quarter wave in length, is found out by using this equation. ZL is what? Your edge impedance. ZO is what? Your impedance which is required over here, that is basically 50 ohm. So using your quarter wavelength transmission line formula, I will find out what is the impedance over here, right? And then you design your microstrip line fade array. Now only the catch over here is, or the disadvantage over here is, remember, this becomes a frequency specific design. This becomes a frequency specific design, and that certainly puts limit on the antenna bandwidth, because at other frequencies that matching is not so called realized. So maybe a VSWR, some kind of impedance mismatching may occur at the frequency which are away from this quarter wavelength frequency. So I have just talked about different types of microstrip line feeding technique, okay, how they are evolved. We have an inset feed first, then we had a simple microstrip line feeding which is directly feeding at the edge impedance, and then we have considered this quarter wavelength section to design the microstrip antenna feed. Now all these feeding techniques actually further led to the two different feeding techniques which are used in microstrip line, that is series fed network and corporate fed network. Now we will talk about their actual application, how the structure is drawn in series fed network and a corporate fed network. This is your series fed array. Now as the name suggests, the antenna elements are fed in series. Means what? Antenna elements are placed next to each other. There is a straight line running, okay, there is a straight microstrip line running, and individually antenna elements are fed at different points. Okay, generally the spacing between these two elements is around lambda by 2, okay, lambda by 2 to lambda by 6, lambda by 2 to lambda by 3, okay, they are depending upon the impedance and the bandwidth, that spacing is optimized, but generally to avoid the mutual coupling we use this half wavelength spacing. Now what is done? This is your input, okay, and this is your input microstrip line running, which is having a characteristic impedance Z0, and the individual microstrip antenna elements are fed in series. Means what? The same element, same signal is being given to all. The same signal is being fed. There is no modification is done. So they are fed one after the other. So first this antenna is fed, next this is fed, and then this is fed, and that's why they are referred to as a series fed network. Okay, they are fed in series. Now what is the advantage is, it's a very simple network to design. Okay, but the problem over here is they are basically realizing a uniform structure. Means what? Whatever power is fed over here, definitely some power is given to this structure. Then the power is coming over here. So power given to this structure is reduce in content with respect to the first element. Further, it is going to the next structure. So power given to this element is further reduced. So that's why maximum power is applied to the first element, then the next, and then the next. This is something very much similar to your series connection of the resistor, right? So you have, depending upon if the resistances are more, of course, power division is definitely happening uniform over there, but here, because this is consuming more power, then there is a loss in this structure because of the finite section of the microstrip line. Then the power is going here, so the power given to this element is lesser than this. So ultimately, it is used in non-uniform array. What is non-uniform array? I will talk about it later. But basically, you can just assume it this way, that there is a non-uniformity in the amplitude of the signal given to the individual elements. The spacing is remaining the same in between the individual elements, but the amplitude which is fed to the individual elements is differing. And that's why it is a perfect example of non-uniform array. And always series fed network, they realize a non-uniform amplitude distribution. Remember this. So maybe a 10 unit signal is given over here, depending upon the losses, maybe a 8 unit signal is given over here and 6. So some kind of an amplitude tapering, some kind of an amplitude as well as phasal tapering. Why phasal? Because the signal is traveling this much additional distance. So amplitude and phasal tapering is happening in case of series fed array. And that's why it realizes a non-uniform array, because individual amplitude or individual phase is varying. Of course, the phase between the consecutive element is remaining the same, right? The phase between the individual element is remaining the same, but you have a phasal level. Like for example, it will be say 10 angle theta, it can be 10 angle 2 theta, and it can be 6 angle 3 theta. Likewise, the phase is increasing, but you have a progressive phase shift. You do have a progressive phase shift, but the amplitude is reducing. So this is the perfect case of non-uniform array, specifically with respect to the amplitude distribution amongst the individual elements, right? So this is one type of feeding network that is called as the series fed array. The next type of feeding network is called as the corporate feed network. Now first just understand what exactly a corporate feed network is by considering the example of 2x2 microstrip antenna array. So this is basically a 2x2 microstrip antenna array. You have 4 elements which are placed next to each other. Okay, these elements are fed at the same edge point. Remember, the other elements cannot be fed over here. The reason is you should be having the similar excitation of the electric field or resonant mode in the structure. That's why these elements should be fed at the bottom side of the individual patch. You cannot have like this mode of connection which is not at all acceptable. Then the polarization or the nature of the resonant field becomes anti-parallel, right? So they are fed like this. Remember, this is the center point of all these arrays. This is the center point of all these arrays. In terms of what? The path length from this point to this point is ensured to be the same. The path length from this point to the individual point is ensured to be the same. And when you have a same path length, definitely the phase distribution is same. Then amplitude reduction is same. That means all the elements are fed with a angle theta. All the elements are fed with same amplitude and same phase. And because of that, it becomes a case of uniform array. Okay, when you want to realize a uniform array, this is the perfect example of the corporate fed network, right? You basically realize all the amplitudes which are fed equally. So how to design this? Definitely you calculate what is the edge impedance over here, then design what a quarter wavelength section, and then have a microstrip line running. Okay, remember ultimately you should have a 50 ohm point over here, 50 or 60 ohm. So definitely these two lines should have a 100 ohm because it is being tapped in the center, or you should have a 50 ohm line here. definitely this becomes a 100 ohm line, right? I'll just explain again. You have to calculate the quarter wave section according to the edge impedance over here. Ultimately, you require this line to be 50 ohm. So this line which is connected in the center or tap in the center should be 100 ohm line, because like two 100 ohm resistor coming in parallel, their tap in center will give me a 50 ohm for this center microstrip line. This is how this array or the power divider circuit is designed. I will not get into the more details of this power divider circuit, but this is general description or brief description about how a power divider and their impedances are calculated. Right? So this is your corporate feed 2x2 microstrip antenna array network. Similarly, it can be extended to 4x4, 8x8 microstrip antenna arrays. Right? Now, as I said, power is equally divided, so it becomes a perfect example of uniform array. Now, in practical cases, remember, in practical cases, I may not be able to realize, or I may not be able to realize all types of arrays using this corporate feed network. Means what? I have just said right now, I am realizing 2x2 array, I am realizing 4x4 array. But if I realize 3x3, definitely the power division may not be equal. If I realize odd arrays, then the power division may not be equal. And in most of the practical cases, depending upon the gain required, you do have the requirement or the design of the array where the equal distribution may not be possible. In most of the practical applications, neither series fed arrays are used, neither corporate arrays are used. What is used is the combination of the series fed and the corporate fed network. Now, one such example, I am just showing it over here. It is basically a combination of the series and the power fed. Remember, the power which are given to these points, definitely they are same in amplitude with respect to each other. But since further over here, power is getting divided, because ultimately these sections, they form series fed network, and that's why the power is further getting divided. So when you realize higher order arrays which requires a combination of corporate as well as series fed network, then naturally it becomes a design of non-uniform array. Remember, most of the practical applications, they design or they use non-uniform array only. One such example definitely I will discuss in the end. Okay, but most of the designs in practical applications, they use a series and a corporate feed network together that realizes a non-uniform array. Okay, but this is very practical example. Okay, so I have discussed microstrip line feed designs. I have discussed the two feeding techniques of microstrip line: series fed network, corporate fed network. Then the more practical case, a corporate feed with a series feed combination, which is more practically used. Now, in discussion with this, now we will go to the difference and the requirement or the advantages, disadvantages of uniform and non-uniform array. Okay. So now we will talk about in brief what exactly a uniform array is and a non-uniform array is. Here, uniform array means what? All the amplitude, rather all the signals or the antenna elements are fed with the same amplitude, and progressive phase shift can be there, but spacing between the antenna elements should be same. So basically amplitude of the signal and the spacing between them should be equal. Of course, in non-uniform array, antenna characteristics, the type of antenna remains the same. There is no non-uniform arrays where I am designing a dipole with a Yagi or a dipole with a microstrip antenna. No, antenna types are the same. But non-uniformity is introduced with respect to the amplitude of the signal or the spacing. More commonly, amplitude of the signal is chosen to realize non-uniform antenna arrays, as we have seen in the combination of corporate and series fed network. So basically different amplitude distributions are used. For example, say I have a 5 element linear array. I have a 5 element linear array. In uniform array, distance between the consecutive elements as well as the amplitude is same. But what is done in non-uniform array? Some kind of a amplitude distribution okay, some kind of amplitude distribution from the center element to the farther element is introduced, okay, that realizes a non-uniform array. Now, going from uniform to non-uniform array, I'll just briefly touch upon 2 points. In case of uniform array, the side lobe level which is observed is always minus 13.6 dB down with respect to the major lobe. What exactly it means? This is your radiation pattern and this is the side lobe radiation. Okay, always in the uniform array, this level is less than 13.6 dB with respect to the main lobe of radiation. Now 13.6 dB down is definitely a quite high level. If you are having an array which offers the unwanted, because ultimately side lobe levels are unwanted radiations. If my side lobe level radiation is causing minus 13.6 dB down level which can interfere with the other radiator, then definitely my antenna is causing the interference. So in such cases my side lobe level should be reduced, or in when the antenna is used as a receptor, I am unnecessarily picking the radiation from the unwanted direction which is quite in good strength. So in such cases I need to have a lower SLL, or it is referred to as a side lobe level. So to realize the side lobe level, smaller side lobe level, basically different amplitude distributions are used, and that is basically the non-uniform array design. You need to create a different amplitude distribution over the aperture of the antenna, okay, that realizes lower side lobe level. Now two such apertures are more commonly realized, is the triangular distribution and the binomial distribution. Okay, so what is done in triangular distribution? The center element is fed with the maximum power, and as you move progressively towards the farther elements or edge elements, the power is reduced in the triangular manner. Okay, whereas in case of binomial distribution, power varies from the center element to the end element in the binomial fashion. Means what, you have a binomial coefficient for number of arrays chosen, number of elements chosen, and with respect to that the amplitude of the power given to those signal is realized. Okay, there are more design details into that, how the binomial arrays are realized, how the triangular arrays are realized, how the elements are designed. These are more design details which is beyond the scope of this particular topic. Okay, so I am not discussing here, but in general what is done, if you have realizing a binomial array, okay, what is generally done, I'll just briefly introduce that. What is required is the aperture distribution should have a reduced gain, or reduced, because ultimately see the power radiated by the antenna is related to the gain of the antenna. Okay, that if you have a smaller gain of that antenna, definitely the power radiated or received is same, rather changes. So what is done purposefully? The gain of the center element is kept to be maximum, and then with respect to the distribution chosen, the gain of the side element is reduced. Okay, one such example is, if I want to reduce the gain of the rectangular patch, I will just reduce its patch width. So if I reduce the patch width and I formulate the patch width in terms of the gain required, I realize that kind of amplitude tapering or amplitude distribution with respect to the binomial or triangular case, and in such cases I realize the binomial array or triangular array. Now what advantages or what effect I am getting here? Definitely in non-uniform arrays the gain of the antenna reduces, right? The beam width becomes wider in nature, but the side lobe levels reduces. Okay, so the price what you pay in non-uniform arrays, the gain reduces, the beam width increases. Okay, but you do get a very low side lobe level. For example, in case of binomial array, you may have a side lobe level which might be 25 dB down as against the main lobe level. Okay, and that's why these non-uniform arrays are being realized. Okay, so this is the example of non-linear array, uniform array as well as non-uniform array with two different distributions which are considered. There are other distributions are also possible, but more commonly these two distributions are being used. Remember, it's a wide topic of research how to realize different arrays or different distributions for a given patch, or rather how to realize the antenna structures for the given distribution. It's a very wide topic, hence it is beyond the scope of this lecture. I am just briefly touched upon what exactly or how this non-uniform structure is being realized. There are a lot of reported papers which are there, one can refer for realizing these kind of configurations. Now in the end, I'll just give you basic one example, very practical example of antenna array which is being deployed in across India also. Everyone is aware about this GMRT, that is Giant Meter Wave Radio Telescope. Okay, it is basically an antenna array. It is the array. Okay, it is an array of dish antennas. If you have visited, okay, this is whatever I am discussing is based on my knowledge of after multiple visits over there. Okay, any student also can visit the GMRT for observing how the antennas are deployed, how it functions and everything. So here it is basically a dish array antenna. What is done in the Y-shaped format? The antenna arrays are distributed and total 30 antennas are present, which are basically covering a meter wave spectrum. Okay, meter wave means what? Right from maybe wavelength lies in meter. Okay, so roughly the band which is covered is from 90 megahertz till maybe 700 or 900 megahertz, where the wavelength is in meters. Okay, I will not get into the more details of what exactly a GMRT is because this is beyond the scope. I am just giving this example because it is a very nice example of the antenna array which is realizing a very large gain. Okay, so here this is the antenna array. It is a planar array. Okay, definitely it is a planar array. Why? Because they are not distributed along one axis, they are distributed along the area. So in all there are 30 antennas. Okay, there are grouping of antenna in the center, and then there are different sections of the antennas which are distributed, and all are uniform. This is a uniform array. Means what? The power is brought together and it is added in the same format. Okay, so this is because the distance between the individual antenna elements along different arms is the same, and it is a case of uniform array. And whatever to best of my knowledge I know, that antenna realizes, since it is tracking, because as the name suggests it's a radio telescope, so it is tracking the intergalactic activity. It requires a very large gain. So what I roughly remember, the gain of the antenna which is realized by this structure is maybe around 40 dBi. That kind of a high gain, because it is distributed over a few kilometers area. Okay, it is situated near a place called Narayangaon, where it is on the Pune-Nasik highway. In fact, as a student, as an antenna enthusiastic, one should visit this kind of a place where you will see an actual practical application of how the antenna array is fabricated. You will definitely, through the visit, you will learn what exactly a GMRT is, what exactly how the antennas are formed, what are different functionalities which are there, and which different bands are being tracked. So this is very, very practical example of this antenna array, where a planar array is constituted. Total 30 dish antennas are, remember, they are there. The size of the dish, the diameter of the dish is around 50 meters. So you can imagine the size and the massiveness of the structure which is there, and that which are distributed, such 30 antennas are distributed over maybe 30 kilometers square range, where it is tracking the intergalactic activity and realizes a very large gain. Okay, so this is one such application. There are many such applications. In fact, near Tirupati there is a MST radar installed by the government, which is also having a very large antenna gain. So here we conclude your antenna array topic. I have talked about the antenna array design with respect to the microstrip line feed, the different types of feeding network, uniform array, non-uniform array, series fed, corporate fed, and the combination of that. And then we have talked about one such example of antenna array which is being deployed in GMRT. So we started with the basics of the antenna, and then we ended up with one such practical example. Many such applications, many such examples are there worldwide. And remember, for all wireless applications, may not be a single antenna will serve the purpose. You need to design the antenna array, and antenna, there are challenges in designing antenna arrays, from dipole to horn to dish to microstrip. Okay, so every design has its own challenge. So thank you. We will now meet in the next lecture.